Section 12.3 is on cylinders and cones. We've already talked about prisms and pyramids. What made a prism was the fact that it had two polygonal bases. And it had lateral faces that were rectangles. Pyramid had one polygonal base. And it had isosceles triangle bases. Lateral faces. So this section here is about cylinders and cones, and what you're going to find out is a cylinder is really nothing more than a prism. Only difference is instead of having two polygonal bases, it's going to have two circular bases that are both that are congruent. And there is no lateral face because it's circular. Okay, so we're going to have LA, we're going to have TA, and we're also going to have V. So let's take a look at a cone. If I can scroll down here. Okay, I'm sorry, a cylinder. So we're looking at a cylinder. First off is it's a right cylinder, which means it's going to be perpendicular from center to center as opposed to oblique. So basically what happens is that this is the center here, this is the center, it's going to be perpendicular, or we can also have right angles here and here. Okay. So we have circular bases, and then the lateral area is going to be the area what's around that cylinder. So if I want to cut this and make it into a two-dimensional illustration, I'm going to cut the top and bottom off, think about it as a can, and then I'm going to cut the can down, straight down through the side right here, and what we're going to end up with is something that looks like this. And this is your lateral area. And I've got my circular base here, I've got my circular base here. So basically the lateral area, LA, is going to be equal to the area of that region right here, which is a rectangle, and we know the rectangle is B times H. So I'm going to call this B right here. The distance across from here to here is going to be my B, and the distance up is going to be my H. And in terms of the actual illustration up here, this is my H, which is the perpendicular distance between the two bases. Alright, and now we need to consider B right here. What is B? Now remember, if I take these two circular regions here and then fold them in and then wrap this around it, we get our cylinder, which looks like a can. So if I wrap that around there, wouldn't the length of B right here also be the length of this circle and this circle, which means it's really nothing more than the circumference. Okay, so how do you find your lateral area of a cylinder? It's nothing more than taking the circumference times the height. So let's go back up to our formulas right here. That's really the same as this right here, instead of calling it P for perimeter, we'll call it circumference. So lateral area for a cylinder is the same as for a prism, which is going to be 2 pi r perimeter times your height. Okay, and again, because we're talking about a cylinder that's always going to have a circular base, we can specify specifically that it's got to be 2 pi r here. So that's your area. Now we also want to find TA. TA is going to be the area, lateral area, plus 2 times the area of the base. Okay. Now that's actually the same formula as our TA up here, but we want to be more specific because we already know the lateral area above is going to be 2 pi r times h. So I'm going to write this out: 2 pi r times h plus 2 times the area of the base. Now what's the area of a circle? It's pi r squared. So notice for cylinders and also for cones when we get to it that our formulas are more specific because we only have one kind of a base here. Are those formulas any different than that of a prism? The answer is no. So if that's the case, then the volume has got to be capital B times H, capital B being the area of the base, which is circular, therefore it's going to be pi r squared times H. So what might happen is you might draw a blank or get a little bit confused here on the area of a cylinder, but remember, if you know the area volume of a prism, all you got to do is modify these three formulas up here to fit what we need down here. And we can do the same thing for cones. Okay, so here's a cone right here. It looks very much like a pyramid. Okay, we always deal with right cones as well. And a right cone has the vertex of the cone directly above the center of the circle. Okay, so that's a right angle. This is your H. This is the radius of the cone, and this right here is going to be equivalent to the slant height L. So what is the lateral area? Well, lateral area of a cone is the same as the lateral area of a pyramid, so it's 1/2 P times L. We have 1/2 here. What's P? P is the perimeter of the pyramid, which is equivalent to the circumference of the circle, which is going to be 2 pi r times L. Okay, and what happens to the 2's? They cancel, so the formula ends up being just pi r L. And again, if you draw a blank for the lateral area of a cone, just think about a pyramid. If you know it, then modify it to fit the cone. So if that's the case, then what is my total area of a cone? That's going to be my lateral area, which is pi r L, plus the area of the base, which is pi r squared, area of one circle. And the volume will also be 1/3, just like for a pyramid. It's 1/3 capital B times H, capital B being a circle, which is pi r squared times H. Okay. Now basically what happens here, just like above, is that if I were to draw another circle that's congruent to the base down here and connect here, we now have a cylinder. Okay. What's the ratio of the volumes from the cylinder to the cone? Well, the volume of the cylinder is how do I write this? So the volume of the cylinder is going to be capital B times H. The volume of the cone is going to be 1/3 capital B times H, which means the cone is going to be 1/3 that of the cylinder, which means 2/3 of the volume of the cylinder is here and 1/3 is within the cone. Okay, so that's a concept, a ratio that you need to know, or it's at least beneficial to know going into the problems. Okay, let me give you a couple examples that you might see. Going back up to this one up here, I might ask you, actually let me just redraw it here. So let's suppose we have a cylinder. I'm going to inscribe a right cone in it, which means that cone is going to come down here like this. Okay, let's suppose the radius here is 5, and I want you to find the volume inside the cylinder but outside the cone. Okay. Let's say the height is 10 right here. Now I can take any one of these figures. I can put a cone inside of a prism. I can do all kinds of different combinations of these 4 different solids. Okay. So basically what we're going to do here is the volume that we're in search of is going to be the volume of the cylinder, and we're going to subtract off the volume of the cone. Okay. Volume of the cylinder is going to be pi 5 squared times 10 minus 1/3 pi 5 squared times 10. Okay, so everything's the same except for it's 1/3. So basically what happens is the volume that we're looking for is really 2/3 of that of the cylinder. Okay, and that was what I kind of mentioned. But if we do the math here, we get 25 times 10, which is 250 pi, minus this is 25 times 10, which is 250 pi. Oops, I better put my pi in. 250 pi minus 250 pi over 3. Common denominator of 3 right here gives you 750 pi over 3. So that's multiplying top and bottom by 3. We keep our 250 pi over 3, and when we subtract, what we get is 500 pi over 3. And that would be your answer. Could give you something like this where we got a couple cylinders where one cylinder is inside the other, so we could call it maybe a metal pipe, and the metal pipe has a thin layer here like this. I want you to find the volume of the metal that's comprised of this pipe here. Okay, so I might tell you the radius here is 4, and let's say it's a rather thick pipe. We'll say the radius here is 5 and 10. So it ends up being kind of the same problem where you're going to take the subtract the volume of the 2 cylinders to be able to come up with the volume of just the metal that the pipe is comprised of. That should be sufficient to be able to get your homework done. Good luck with it.